So I've decided to give a Blackboard talk after all, otherwise I'm a bit, I would be too quick. Today I want to tell you a bit about some obstructions that I found to those ideas in the algebroids. And along the way, obstructions to representations up to homotopy. So we'll define those representations up to homotopy. So recall that we had a Lie algebroid A over M and an infinitesimal ideal system, and A was triple Fj nabla, where F is an involutive subbundle of Tm, so that's basically the reduction of the base. J is a subalgebroid of A. That is the fiber you want to kill when you think about ideals as reduction. And it needed to be anchored at F. And you needed a flat F representation on A mod J in order to do parallel transport along your foliation and reduce the bundle A mod J along the leaves of F. So except those three things, well, if you think about J, first of all, as a subbundle, this is really the reduction, geometric reduction of a vector bundle. And then when you add here subalgebroid, here J anchored in F, and then this ideal condition that this time I've written like this, that the connection makes the bot connection of J geometric. I mean, it's up to the anchor. It's the connection of the bot connection of J. Then you have this ideal structure, right? Well, I'm cheating a bit. So if you had equality here, that would suffice. But if you don't have equality, then you also need to know that flat sections bracket to flat sections. So I'm going to tell you first about a simple result in terms of the Artia class of a Lie pair. Then we'll talk about the Pontryagin characters of vector bundles, and then of graded vector bundles, and then we'll see those Pontryagin obstructions. So first of all, the Artia class. So that's Sieno and Shu, 2016. They define the Artia class of a Lie pair. So what is a Lie pair? If you have A, J, Lie pair, so that means that this is a Lie algebroid over M, and this is a subalgebroid of A over M. So that's just a Lie pair. Lie algebroid, a subalgebroid. Then if you have such a Lie pair, then how should I formulate this? You have an Artia class, so you have a cohomology class. Alpha J, so it's in cohomology of J, the Lie algebroid J with values in hom, A mod J, and A mod J. So you can also write it as a tensor J0, J annihilator, tensor J annihilator, tensor A mod J. With respect to what? Well, you have J with its flat representation on A mod J, the bot connection, bot representation. So you combine it to, well, you take the induced representation on this space, right? So I'm just going to write it like this. So this Artia class, I'm going to write how it's defined. So it's a cohomology class in here that vanishes if and only if there exists, let me think, yeah, if and only if there exists an extension nabla, so an A connection on A. It's not a representation. If I talk about an extension, I didn't write extension, so it's a connection extending nabla J, meaning that it's going to preserve J when you restrict it here to J, and then the quotient connection is the bot connection. That's easy. You can always choose such an extension. such that, well, whenever A and B in A mod J are nabla J flat, then this extension nabla AB is also nabla J flat. So that's a strange, well, maybe strange conditions, not very geometric. And they use that in a completely different context as I do, and I don't want to explain it because I still don't understand what they do with that. What I noticed is that this ATIA class gives us an obstruction to J being the fiber of an ideal, and that's what I want to explain. So I have a very, very simple interpretation for their very complicated stuff. I mean, the class is simple, but whatever they do with that, I will learn in the next 5 years. So how is it defined? It's very simple. You take alpha J is the cohomology class of omega nabla, and omega nabla is the one J form with values in hom A mod J and A mod J. That's one too much, is it? No? That is well defined by omega nabla of a J and of an A bar and of a B bar is A nabla J A B bar. So you have your extension, you look at the curvature, and you notice that this is, I mean, defining this form like this is well defined because A nabla J is vanishing. So whenever you have J1, J2 here, this is going to vanish. So this form is well defined. Anyway, that's this form is defined by the curvature of the extension, and checking that it's a closed form is just I don't know, 2 or 3 times the Jacobi identity and things vanishing. It's immediate. And by the way, it's really an adaptation of Atia's class of a holomorphic vector bundle, right? It's exactly the same construction, just that you have a leap pair instead of a holomorphic vector bundle. So now we do exactly the same. And you take, so F, J nabla, IIS in A. So say you assume that you had already J from the leap pair, but you assume that you find an F anchoring J, and you find the flat connection anchoring the bot connection. And take an extension now. Again, what am I saying? It's an TM connection on A. Oh, and this okay, sorry. I should give different names to all those things. So let's say this extension was nabla. No, because that's the other one. Well, okay, nabla tilde, and here nabla tilde. I want to talk about all those things. And here, say this is nabla tilde tilde because I don't have a better idea. So that's an extension of the IIS connection. Right, so this is what should be called nabla. Same thing, it's just a TM connection on A. It's not a representation anymore. You lose the integrability. But whenever you have a section of F here and a section of A, you land in J, then you have an induced quotient connection, and this quotient connection is your IIS connection. And then define same omega nabla tilde. Now it's going to be a one form, an F form with values in hom TM mod F and A mod J by exactly the same formula. Say so. Omega nabla tilde tilde of some, well, let's say X in F, class of Y and class of A is again A nabla tilde tilde of X Y, A, and the class of it. So that's now a form in this space, and again, it's the same computation, you just replace letters. 2 times or 3 times the Jacobi identity, n terms killing each other, give that this is closed. And then you have the Atiyah class alpha, did I call that one alpha J? Yes, so let's call this one just alpha. In the F cohomology with values in hom, T mod F, and A mod J. So that's the Atiyah class of the IIS. Right, and I forgot to say in both cases, of course, I say the Atiyah class, it doesn't depend on the choice of the extension, right? It doesn't depend on the choice of the extension. So it's really the class of the system, of the Lie pair or of the infinitesimal ideal system. But now this one is much more geometric. So, and this one is the one that I see actually more as directly generalizing the holomorphic context. So you have that alpha vanishes if and only if there exists an extension nabla tilde tilde of nabla such that whenever, or what was it? Whenever Y is a vector field on M and A is a section of A such that the class of Y is nabla flat and the class of A is, that's nabla F, that's the bot connection defined by F, and the class of A is nabla flat. See, we already have 5 different connections here, right? We also have that's the connection of the bot representation defined by F. By the way, you should have interrupted me here. No, that's alpha. That's alpha of the IIS. Right, so we have alpha sub J, that's this construction that's living in this cohomology that is just defined by the bot cohomology, the bot representation defined by J. What I forgot to say here is that here I didn't write a connection. It's because F is represented on Tm mod F by the bot representation defined by F, F on Tm mod F. And it's also represented on A mod J by the IIS connection. So this is really the cohomology defined by a representation, which is a combination of those 2 representations of F, right? So now the alpha vanishes if and only if those 2, you find a connection that is going to combine flat sections to flat section. Right, and I say this is much more geometric. You're not happy. So it's going to vanish if and only if whenever you have a vector field Y on M, the class of which projects to the leaf space, basically, if the leaf space exists, that's this nabla F flatness. And whenever you have a section of A that would project to a quotient vector bundle, that's the nabla IIS flatness, then the value of the connection, so this extension of Y on A, would also project to the quotient. That's again nabla flatness. And that's why I say it's very geometric, is because whenever you have an IIS such that you have a reduced vector bundle, well, you have this, because you just take a connection on the quotient and pull it back.
There's too many connections here.
Yeah.
Connection.
So that one is the extension of the IIS connection.
The tilde
is it's a classical TM connection on E. And it's the extension of the IIS connection. right? So I got that dilemma, and it's not really due to me. I mean, I think it's folklore.
Sorry, so is it correct that then if you take the specific infinitesimal ideal system where you have f nabla f, then this Atiyah class would coincide with the one of the Lie pair, which is just Tm and the subbundle?
And then it would be Molino's Atiyah class from the 70s. The Atiyah class of foliation.
Okay.
So, lemma, if you have f nabla j iis in am, so if the quotient, I should have used slides. I'm really slow. So if the quotient vector bundle A mod J mod nabla over M mod F exists, then there exists such a connection. So then the Atiyah class alpha of F J nabla vanishes. That's pure geometry. That has nothing to do with the algebroid structure. Right? I mean, it's really that you have a quotient vector bundle. And then when you have this, you consider, again, you assume that you have an infinitesimal ideal system, otherwise it doesn't work. And you define the map rho star from one complex to the other. So hom M mod F and A mod J to omega bullet J, I mean the other one, which is simpler, and A mod J. Just by saying that rho star of a form here, eating K sections of J is going to be omega of, sorry, I need to write as well class here. Yeah, I need to write much more than this, like this. So it's omega rho on the elements of J, and then you apply it to the class of rho A, and B, you let B because this and A mod J is the same. So anyway, the anchor, whenever you have an IIS in A, then the anchor defines a cochain map here. If you don't have an IIS, it doesn't work, right? So that's not always a cochain map.
The leaf space of the foliation, M over F is the leaf space of the foliation defined by F?
Yes, that's the leaf space of the foliation.
What do you mean by X exists? You mean? You said if the
whenever this quotient vector bundle exists. I mean, whenever this is smooth manifold, and nabla has no holonomy, so that you have a reduced vector bundle. It doesn't need to be smooth.
You mean the regular foliation, yes?
I always mean regular foliations, but then here I mean the simple, so the least space.
Simple, yes,
yeah.
simple.
Yeah. Right. So that's a cochain map. And then that was actually a lemma. And then the theorem, and that's, yes, that's to me, but I still didn't publish it. It's on archive, but it has been on archive for 6 years. So if, and it's not because I submitted it and it was rejected, I just didn't submit it yet for some reasons. So if you have an IIS in A, then rho star sends alpha to alpha j. Right? I mean, rho star the map in cohomology. And that's again a very simple computation. And so as a corollary, same, you get that if you have if you have a AJ, a Lie pair, such that J Let's write carries an IIS fj nabla such that, well, A mod j nabla, M mod f exists, then alpha j has to vanish, right? Because you know that the ATIA class of reducible IIS, reducible in the sense that geometrically the quotient vector bundle exists, the ATIA class always has to vanish. And whenever you have an IIS, this cochain map, so the anchor sends your IIS connection to alpha j. So if you have a reducible IIS, alpha j has to be 0. So this ATIA class of the Lie pair defined by Chen, Stieno, and Shu just gives you an obstruction to j being a fiber along which you can reduce your Lie algebroid, right? And that's a very geometric interpretation. But of course, it's not it's necessary, but not sufficient. And by the way, I didn't say, but those IIS, infinitesimal ideal systems, they are really infinitesimal versions of Mackenzie and Higgins ideal systems from the 80s. And that's really the correspondence. Whenever your infinitesimal ideal system is such that there's a reduced vector bundle, then your infinitesimal ideal system integrates to an ideal system in the sense of Mackenzie and Higgins. That's the correspondence. So one could say whenever J is a fiber of an ideal system in the sense of Mackenzie and Higgins, then the ATIA class of the Lie pair defined by J has to vanish. Okay, so that's the first obstruction. But as I have said, it has actually not much to do with the, well, it has some things to do with the Lie algebroid structure of A, but the key really is geometric. It's just about this quotient vector bundle existing. And then you use, of course, the anchor, the Lie algebroid structures to get your classes and so on. So I want to show you another set of obstructions. So I'm going to start here, and you're going to remind me not to erase what I'm going to write now. So we want to talk about Pontryagin characters of a vector bundle. And that's going to be a crash course. I decided not to give details, just the construction. And that anyway. So recall that a linear A connection on E is an operator, or amounts to an operator D nabla, which takes A forms with values in E and send them to A forms with values, A forms with values in E of degree increased by 1. Right, so we defined, of course, an A connection on E is defined as I've written before, but we've seen on Monday that it's the same as such an operator, and the operator squares to 0 if and only if the connection is flat. So if and only if the connection is a representation. So E nabla square is 0 if and only if the connection is flat. Right. So whenever you have this, I'm going to write it here. And that's the part I need to keep for later. So you look at this, this D nabla square. So D nabla square, when it's not 0, it's actually a 2 form on A with values in endomorphisms. Well, what do I mean by that? D nabla square amounts to the curvature of the connection, and how does it work on forms? You basically just compose the end part, you just compose the E part of the form with the endomorphism, right? So maybe I should, well, if you don't ask me, I'm not going to write details here, but d nabla square is omega A linear, and then it just amounts to wedging your forms with such an element. And such an element, you can also take powers off just by, wedging the form parts and composing the end parts. That's relatively easy. And you get, for each I, the I power of d nabla square, and that's then a 2I form with values in endomorphisms of E. Right, so what is the property of these 2I forms? The property is really the magie of the trace. So if you have a form with values in endomorphisms, you can compose the values with the trace operator, right? On endomorphisms, you always have the trace operator. So composition with the trace operator, for which I write trace. So it's in gamma and E to R, and that's actually omega 0 A blah blah blah. That gives, and really that's really the magie of the trace of a product of a matrix being the trace of the other product, the other way around. So it gives the classes trace of d nabla 2I. So because I have composed, I have killed the end part to give an R, they just become 2I forms on A, right? So you just get forms in the complex just defined by A with a trivial, the canonical representation on R. And those forms are automatically closed. So dA trace of those powers I are all closed for I greater than 0. And it would have been better to have just slightly more space. But the classes the classes dA is 0, so you have classes, you have cohomology classes. They don't depend on the choice of the connection. So this is in a 2I cohomology of A, and they do not depend on the choice of the connection. Right, and those classes I call sigma A 2I of E, because they don't depend on the connection, and I name them the A, well, it's not me, sorry. They are exactly the A Pontryagin characters of E. The Pontryagin classes would be some combinations of these, right? So you have those Pontryagin characters, and obviously, I mean, I guess the silliest, not silly, but the most immediate interpretation is, well, if E carries a representation of A, then this is 0, so all those powers are also 0, and then all those cohomology classes are 0, right? If you have a representation, all Pontryagin characters vanish. But that's very, very rough information that you extract from there. And that's somehow, in my opinion, not enough, because you can explore what those characters tell you. So let's keep this board, and let's keep that one, and let's get rid of that one. So I'm going to write the theorem by Bott from 72. That's in his lectures on characteristic classes and foliations. That's also where he defines his bot representation, probably not knowing that now everyone would talk about bot representations in all well, not all contexts, but many contexts. So this theorem by Bott from 72, or maybe a bit earlier, because I also always have the version from his lecture notes. It's probably 69 or something like this. It gives an obstruction to the integrability of a subbundle of the tangent of a manifold. And because subbundles of the tangent, well, involutive subbundles of the tangent are prototypes of ideas, I was thinking that this could generalize to obstructions to ideas in the algebroids. So that's Bott and, well, 72 or before. So if you have a smooth manifold and F, a subbundle of codimension Q, then if F is involutive, then let's write it in my notation. Then all those Pontryagin characters have to vanish. So in that case, they are Tm. A is Tm, it's the classical situation. Sigma Tm of the normal bundle Tm mod F have to vanish for all I greater than the codimension. Okay, so that was this result that I was hoping to generalize to the context of ideals in the algebroids. Why? Because he starts with a subbundle and then he finds an obstruction to F being involutive in terms of the Pontryagin characters of this normal bundle, right? But the thing is, when you look at the statement, you don't really know where the involutivity is important. I mean, is it in the construction of the classes or is it really in this space? And actually, it's in the construction of the classes. So if you look closely at the theorem, you can get my modern version. So theorem revisited, say. And that was published in 22. So if you have A, the algebroid, with B and A, well, actually, AB is a leap pair, so I should call it J, but whatever. So B and A is a subalgebroid of codimension Q. So if E over M is a vector bundle with a representation of B, so of the sub-object, then the classes sigma A to I of E have to be 0 for all I greater than the codimension of Q, right? So what you notice if you look closely at his statement and the proof, and I'm going to give the proof of this result, is that it's actually not very important what is there. What is there should be just a vector bundle with a representation of a sub-algebroid of Tm that has codimension Q. Right, so sketch of proof is very easy. Actually, it's almost a proof, but and also, again, it's just taking his proof but replacing letters, right? So no credits for me. So sketch of proof, you take the representation nabla of B on E, and then you extend it again, but now it's easier because it's just an extension. You just complete it outside of outside of B on the complement of B. So extend it to an A connection. Now, there's just one tilde. Nabla tilde is an A connection on E. Then this D nabla square, nabla tilde square, which is R nabla, it's going to be in I2B, tensor, gamma, and E. What is I2B? That's the differential graded ideal of forms that vanish on B, right? So that's omega in omega 2A. Oh, no, I always need to think. It's the forms that are generated, so they vanish whenever you feed them with two sections of B. Right? If B was a if A was TM and B was an involutive subbundle, that would be this differential graded ideal that is equivalent to the involutivity of A. Right? So whenever you have that, then this form is vanishing on two sections of B, because when you restrict it to sections of B, well, it's the curvature of nabla, and the curvature of nabla vanishes because it's a representation. It's very easy. And then you get that D nabla tilde to the power 2I is in I2B to the power I, tensor, gamma, and E. And so the trace, those traces, they are actually in I2B to the power I. But because B has codimension Q, you have that the dimension of B0 of the annihilator is Q, and this ideal is generated by B0. So if you have too many powers of it, it's vanishing. That's it. Super easy, right? So if I is greater than Q, I to B to the power I is 0, and that's it. But that's not logical. So you have the statement. So you have that those forms must be 0. B0, sorry, is the annihilator. So that would be I1B would be sections of B0. So that's the annihilator of B. Okay, so we have this statement. And then it's a good start, but it's not good enough because, well, recall now the IIS. F, A, nabla, IIS. Then you have 4 different representations defined by the IIS. So you have so 4 representations. So you have nabla F, which is an F representation on Tm mod F. So that will give you the classical obstructions of bot, right? If you have this representation, then all the Pontryagin characters of Tm mod F in the Tm cohomology, the RAM cohomology, will have to vanish from a certain point on. Then you also have nabla J. Now, that's a representation of the subalgebroid J of A on A mod J, so you will have that the Pontryagin characters of A mod J in the A cohomology will have to vanish from a certain point on. You also have, well, the IIS connection, so F on A mod J. Again, the Pontryagin characters of A mod J in the RAM cohomology will have to vanish from a certain point on, because F is a subalgebroid of Tm. And what is far more, well, it's not difficult, but it's not obvious, is the fact that you also have a J connection on Tm mod F, which is flat. Just by an F, by composing this one with the anchor representation. So you have 4 representations, which are representations of sub-algebroids of Tm and A, so you get all sorts of Pontryagin characters, but they're not good enough, in my opinion, because they are Pontryagin characters of normal bundles, first of all. So if you want to start from less information than already knowing normal bundles, it's not enough. And most importantly, they don't really talk to each other. I mean, they are related somehow by the anchor. I mean, I don't remember some of them. I mean, this one is related to this one, obviously, because, no, this one composed with rho. But when you look at the proof, you've just used the fact that J is a subalgebroid of A, that F is involutive, and that nabla is a flat connection. You have not used your ideal condition. So there's more to get, right? And in order to get more, you have to go to the world of representations up to homotopy. And I'm going to write.
Number 4 are intertwined by the anchor. Number 2 and number 4 are intertwined by the anchor.
Number 2 and number 4.
I mean, the second and the fourth.
Yes. But let me check here later.
But we denote it by the same letter, so I cannot.
Oh, sorry. Yeah. Just give it another name. Yeah. Sorry. Yeah. Okay. So, I think someone said it. It was Francesco. We have no adjoint.
Yes.
Yes, it was Francesco. So, big problem in the context of the algebroid. So if you try to define the adjoint representation and hope to, well, bless you. If you hope to define an adjoint representation by saying add AB is nabla AB, you will not get a flat A connection on A, right? It's not going to be a representation of A, right? So this is not a representation. I mean, it's not even it's well defined, but it's not a representation because it's not infinity M linear in this argument, right? If you multiply F with a smooth function, it's going to be here. It's going to come out with a differentiation along rho B. So in the context of the algebroid, we don't have an adjoint representation, but we have an adjoint representation up to homotopy. Right, so this one we keep, maybe up there. And in order to define representations up to homotopy, we're going to start by defining connections up to homotopy, which are, for some reason, much less studied, I mean, considered. We'll go to iterator representations. Right, so connections up to homotopy. So you take now a graded vector bundle. Janusz is not here today. I would have got a question here. Graded vector bundle. How do I want? No, let's just call it E. I don't know why I want to bar. So graded vector bundle concentrated in finitely many degrees. So graded vector bundle is now a direct sum of vector bundles over a common manifold, and you just assign degree 0 to the first one, then degree 1, etc., and you go to degree n minus 1. Right? So it's a graded vector bundle concentrated in n degrees. You start at degree 0, and then an n connection of a Lie algebroid A over M, I should say is over M, on E is an operator D. So what does it eat? It eats A forms that you cannot really change, but with values in E. And now if you have an A form with values in E, you're going to have a form degree, but also a degree of the image of the form, right? Because the E has several degrees. So we're not going to talk about the form degree anymore. We're going to talk about the total degree of a form. You add the form degree and its image degree wherever it lives from. So you take an operator like this that now increases this form degree by 1, and that satisfies D of omega wedge eta. Now again, this is just an A form, no secret here, and this is an A form with values in E. You have the same Leibniz formula done for a classical connection, a one connection. Omega wedge d eta. So that would be an n connection or n-term representation of the homotopy, but that name seems to annoy some people. So an n connection, and it's an n representation. D is an n representation if d squares 0. So let me write a couple of examples. I think I'm going to finish on time, but you will not have time for questions. Yeah, you can interrupt me when
yeah. Is it n connection? N is an aberration or something? Or why is it called?
Because you have n bundles, but you start grading in degree 0.
So stupid. Okay.
It's because if you just have E0, no degree, you want it to be one connection. I don't know if it's a reason, but it's consequence. Yeah, sorry, that was German. So, examples. The easiest example, obviously, is if you have for I equals 0 to n minus 1, nabla I, an A connection on EI, and then you're just going to take d nabla of omega. It's just d nabla I omega if omega lives in, is a form, well, has values in EI, right? So you just take a connection on a graded vector bundle that preserves the degree, right? No, I mean, then this operator is actually going to increase only the form degree. It's not going to look at the vector bundle degree, right? That looks very silly, but it's the key to the main theorem. And then in general, if you have n equals 2, so E equals E0 plus E1, then you would have D of a section of E0. So E0 is in E0, so it's a 0 form on A with values in E0, so that has degree 0. So the D has degree 1. So degree 1 can be either, again, given by some, let's write like this, D nabla 0 of E0. So that would be a 1 form on A with values in E0. But it can also be a section of degree 1 that we're just going to call partial E0. That's a section of E1. So if you have a 2 connection, its values on forms of degree 0, of total degree 0, so on sections of E0, is given by an A connection on E0, and then vector bounded morphism E0 to E1 over M. And then similarly, if you start with a form of degree 1, and then it's also enough. It's enough. Oh, okay. Can someone get a board? Yeah, thanks. So this we keep, this we remove. So on a section of degree 1, you would have, well, no vector bounded morphism going to degree 2 because there's no degree 2, but I'm just going to write it. Would have D of E1 is again D nabla 1 of E1, so you have an A connection on E1. And then you have some omega eating E1, and that would be a 2 form on A with values in E0. So the omega is a 2 form on A with values in hom E1, E0, whatever. So a 2 connection is given by 2 connections, but also 2 operators which allow you to switch degrees. And then D square is 0 if and only if those 2 connections and the vector bound morphism and this omega, this curvature, satisfy together some conditions, right? And here lives the adjoint representation up to homotopy. Up to homotopy of a Lie algebroid. So it would be D A0 in degree 0 plus Tm in degree 1 to itself, but increasing the degree by 1. Right, so you can make sense of the adjoint representation up to homotopy of a Lie algebroid as a 2 representation, and it's actually always given by a choice of Tm connection on A, but then it's very simple. It's really de-singularizing this ad I was trying to write to something that is well-defined and is a 2 representation. And then the theorem, I can mention along the way, that's with Ortiz and Drummond. And it must be published in 2015 or something like this. So if Fj nabla is an IIS in A, then D restricts, so this D adjoint to a 2 rep of A on J0 plus F1. So an ideal in a Lie algebroid is a subrepresentation of the adjoint, right? So we have covered all the things that an ideal in a Lie algebroid should do. It gives you reduction, it gives you the special foliations in a tangent of a Lie algebroid, and it gives you a subrepresentation of the adjoint. Right, so that is going to give us an obstruction because let's use that board. In general, you have, when you have an N connection, you have your D square. It lives in omega A and E dot graded E, some total degree. Then you can take its powers, same thing. Sorry, that's total degree 2. Then total degree 2i, you can take its powers, works the same. And then here, you're going to compose with a super trace operator. So you have end E, end of a graded vector bundle that has all the endomorphisms of the components. So E0, E1, etc. It also has mixed terms. So hom E0, E1, for instance. And the super trace is just looking at the ends on the diagonal, and it's putting a sign in front of, so end E0 would have positive sign, and E1 would get a minus sign, and E2 would get plus, and so on. So that's the super trace. It's just a trace, but signed. So let's call it like this, super trace. It gives same Maggi closed forms. There's nothing to do here, just adding degrees and replacing the trace by the super trace, and you get the Pontryagin characters of the graded vector bundle, and they don't depend on the choice of D. So again, almost nothing was done here, just replacing stuff. But what you get is that if D is a representation, is an N representation, then all those characters have to vanish. But what you also get immediately from example 1 and that's the main theorem, which surprisingly had not been seen. So surprisingly and very good for me, no one had seen it, but get a very nice result, which I'm almost done. So if you take example 1, you have D square is somehow a nabla 0, a nabla 1, etc., a nabla n minus 1, right? So D square is a two-form on A with values and endomorphisms of E, but if you just had diagonals and no mixed terms, then D square is just a diagonal matrix with all the curvatures of your connections on the diagonal. So D square to D to I just looks like this. And then the super trace of D to I is sum I equals 0 to n minus 1 to the I trace of a nabla 0I. That's it. Again, very simple proof. And then you get a wonderful theorem. E, a graded vector bundle. Then for all I greater than 1, you have that the Pontryagin characters of E in degree 2I are the alternating sums of, with signs, alternating, sorry, of the Pontryagin characters. No, that's not the, that should be a different one. So let's call this one J, EJ. So the Pontryagin characters of a graded vector bundle are just the alternating sums of the Pontryagin characters of the summons. And in particular, that's also 2022, in particular, if E is E00 plus E11, and if it carries a 2-rep of A, then you have that sigma A to I E0 equals sigma A to I E1 for all I greater than 1, right? Because you have this formula for the Pontryagin characters, but if you know in addition that E carries an N representation, then this is the formula for the Pontryagin characters given by this choice of N connection. But if you take as a choice of N connection your N representation, then you get in addition that all those signs, the sites will vanish. And then you will have, in general, that if E carries an N representation, then the alternating sums of the Pontryagin characters will have to vanish. And in particular, if you only have 2 summons, and E carries a 2 representation, then you have that your 2 summands will have to have all Pontryagin characters being the same, right? And I see that really as a new, maybe modern interpretation of Pontryagin characters. What do they tell us? They don't tell us only, well, if a vector bundle carries a representation of A, but if 2 vector bundles can carry together a representation of A, right? Because if you don't have this, for 2 given vector bundles, they will never carry a 2 representation together. And now I come to the point. Why is that useful? It's because if you have now just a choice of J and of F, so assume you have a Lie pair, you find a candidate for your involutive subbundle. If J and F don't have all Pontryagin characters the same, then they will never carry an ideal together, right? But I don't write it because my time is up. Sorry for the over time.